Now we're going to have a little look at some of the numbers that are in the model and how those numbers affect the spread of the disease. So we're going to have a little look at these numbers here. The first one we're going to have a look at is this one, immune prob equals 2. Immune prob is sort of the name of the number and 2 is the value that we've given it. Now what this controls is how many of our cells initially are immune, what the percentage chances of any cell being immune, so that when we're setting up the board we know whether our cell is susceptible, green, or immune, blue. What we can do is we can change this number. So for example, let's change it to something like 80, so that now we have an 80% chance of a cell being immune, and see what change that makes to our simulation. So as you can see, with such high immunity, only a very small proportion end up being infected. Okay, so let's put this back to what it was. It was 2 to begin with. You can always leave yourself notes in the code to tell you what things do, which the computer will then just ignore. So this is the chance that a cell starts out immune. We're using curly brackets for those. Okay. Let's run it again back at 2 and see, yep, we've got back to our usual system. Another number that's very important to our model is this one, recover prob. So this is the probability that when an infected cell is selected by the model, that cell recovers. So at the moment it's set to 15%. Again, we can change this. So what if we set our recovery probability to be very high? Let's say 90%. So chances are when an infected cell is selected, it will recover. What is that going to do to our disease modelling? Well, as you can see, that was very brief. We have only a tiny proportion infected and the disease burnt itself out very quickly because those people who were infected recovered very fast and had very little chance to infect anyone else. So that's what our recovery probability does if it's very high. What instead if it's very low? Let's set our recovery probability to 1%. And if we run that, then what happens? So you can see the disease is spreading very quickly. And if we just wait for it to run its course, what we'll find is that actually no cell escapes. With a recovery probability this low, the chance of every neighbour being infected is just too high. So the disease will work its way through the whole population eventually. That's what recover prob does. It changes the probability of a cell to recover. Now if we want to make another change, we either have to wait for the simulation to finish or we have to halt it. And we can leave ourselves a note here again. So this is percentage chance that a cell recovers when selected. Very good. And let's put this back to 15 so that we're back where we were. There we go. Looking familiar now. We've got two numbers left here now. We've got start radius equals 10 and infect prob equals 1. Infect prob is the probability, the percentage chance that a given cell is infected to begin with. But against that we have the start radius. So this determines how far away from the centre of the board the disease can start. So if we massively increase the start radius, so if we set it to even just 50, what we'll find is that the disease can start in lots of places at once and will spread in a very different way. Equally, if we change that back to 10, but we increase the infection probability, well, you can probably guess what would happen. So this is now a 1 in 2 chance that any cell within the start radius is infected. We have a lot of disease to begin with that then spreads outwards. So there we go. The start radius is the distance from the centre that the disease can start. And the infection probability is the probability that a cell starts out infected. And of course, that's only true for cells that are within the start radius. And as we go through a bit more of the code later, you'll see exactly how those two come together. So there you are. Those are the main controls for our model, the main things that we can change that will affect how the disease spreads. So now have a go at changing them for yourself. See if you can predict what certain changes will do. See if you can make interesting patterns emerge. Can you find a set of values where you get big pockets of people who end up not infected at all? What values do you need in order to get the whole population infected? What happens if no one is immune to begin with? What changes then? There are lots of interesting questions and interesting answers that you can get out of this simulation by changing the numbers that are in your model.